some basic things in organic chemistry. Um, let me record. We also talked about how to name some organic compounds. Um, we talked about homologous series and so on. So today we'll be continuing from where we stopped. Okay, still on hydrocarbons. We'll be extending from the basics of organic chemistry to more complex things, I guess. Okay, the last time we talked also about um, primary, secondary, and tertiary alcohols, what those things mean. Okay, in this class, we would also be talking more about different functional groups. Okay, and how to name them, their reactions, and so on. So right on your screen, what you can see is one of the previous year's past question. Okay, some of you that might have been studying your past question might be conversant with, or this question might be familiar to you. So when we talked, just to recap or remind us about what we talked about in the last class. Okay, if I have this kind of a structure, so if I have this kind of a structure, what type of alcohol is this? Is it a primary alcohol, a secondary alcohol, or a tertiary alcohol? It's just a straightforward question. I just need a single answer, and then we'll move on. Yes.
A primary, ma.
Why is it a primary? Why did you say it's a primary?
Only
Okay, if you
containing one group.
one what?
Carbon group.
Very good. That's a very correct definition. Now use that your definition. We said that primary, okay, very good, but not totally accurate. We said primary alcohols are alcohols that where the carbon attached to the OH group, which is the functional group, okay, is having just one carbon group to it. Or rather, we can say just one alkyl group, alkyl. Okay, so now this is the carbon that the OH is attached to. This carbon I'm writing with a black C. How many other carbon groups is it directly attached to? This is one bond directly attached to a carbon. This is another bond directly attached to another alkyl group. This is a last carbon directly attached to an this is the carbon directly attached to a third alkyl group. So with your definition and with what we know um primary alcohols to be, this is totally not primary alcohols. We can see three alkyl groups attached to the carbon carrying the OH group. So what can we say? What is the correct answer?
Primary
Tertiary, ma.
alcohol.
Very good. Tertiary, well done, the both of you. So over to what we have today. In organic chemistry, we also have what is called isomers. Okay. Now isomers tells us that two structures, okay, we can have structure A and structure B. Isomers is saying that we are judging these two structures by their structural or compound A and compound B, okay? So let's say we have compound A and we have compound B. Now we are judging these two compounds by their structure, okay, which is also called structural formula, and also by their molecular formula. Now we call isomers is called when two structures have different structural formula, or two organic compounds have different from structural formula, but their molecular formula are the same. Okay, so what do we mean by that? For example, we have this structure here. Okay, and we have another structure. Okay, so this one has 1, 2, 3, 4, 5, and then the hydrogen. Sorry, please excuse me. Okay, we have this, and this can be summed up to be 1, 2, 3, 4, 5, and the age is 1, 2, 3, 4, 5, 6, 7, 8, 2, 4, 6, 8, 10, 12. Okay, and the next one we have. So now we have these two structures. Okay, now if you look at, oh, I'm repeating the same thing. This is hydrogen here. Now, if we look at these two structures, okay, they're not exactly the same thing, right? Because if you look at them, one, 1, 2, 3. Sorry, please excuse me. We have one more carbon. If you look at the first structure, it's a straight chain, okay? And what we will call this structure is butane. Why is it so? Because it's having four carbons in a straight chain. There is no other functional group aside alkane. But if you look at the other structure, we can't name the second structure a butane, right? Because the longest carbon chain can go like this. Okay, so we have 3 as the longest carbon chain. It's going to be propane. And this one at the top, this carbon at the top will now be a substitute. So this will be methyl propane or propane or 2-methyl propane. So these are 2 different structures. Take notes of what I'm saying, structures, but then their molecular formula, that is to tell you the total number of carbons and the total number of hydrogen that makes each of this compound. That's what molecular formula is all about. Their molecular formulas are the same. Why is it the same? How many carbon do we have in butane? 4. How many hydrogen do we have all together? We have, let's count it all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 hydrogen. This second one, how many carbon total? 1, 2, 3, 4. Then how many hydrogen total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 from this H3. So it's also H10. So now you can see their molecular formula, if you're writing their formula, are the same. So isomers is when 2 elements have the same structural formula, sorry, different structural formula, that is in their structure. If they draw the full structure, they are not looking exactly the same. Okay, but when you count the total number of molecules, carbon and hydrogen and oxygen or wherever is there, that makes that compound is the same for the 2 things you are relating. Okay, I hope that's understandable. Now there are different types of isomers. Okay, we have, take notes, structures are different but molecule is the same. Okay, so for your level, we have chain isomers. Is the example I just gave now. Another one is we have position isomers. Now, how do you differentiate this? Position isomers. Okay, let's just go on. Functional group isomers. Okay, and another one is we also have geometric isomerism. Excuse me. Okay. Now, geometric isomers usually occur in double bonds, okay, in double bond saturated compounds. Sorry, unsaturated compounds that have double bonds. Now, chain isomerism, it just has to do with the chain. The chain is maybe for one of them is branched, the other one is straight, just as we can see in this example we did earlier. Okay, we can see that the butane is a straight chain hydrocarbon, while the methyl propane is branched because there's one substitute at one place. Okay, so that branch chain is now making a substitute rather than a part of the continuous longest chain. Now, position isomerism have to do with when you see 2 structures that are having the same functional group. Don't mix this up with functional isomerism. It's the same functional group, okay, that are in the two structures, functional group. But the difference is the position of the functional group. Okay, so the difference is in the position of the functional group. So the functional group, okay, so for example, we have this structure. Okay, and then we have OH here. And we have another structure. Okay, what is in all these other places are hydrogen. Now, if we are to name these two structures, they are not exactly the same thing. You know. The difference is the position of their functional group. This first structure and the second structure, they are going to have the same molecular formula. That's what makes them isomers. But their structures are looking different. Okay. Now, if we are to name this A, we are not going to give it the same name as B. Why? Because their structures are not the same. So the difference in structure also tells you or explains the difference in the naming. Okay, so this first structure A will be called 2 um but 2-butanol. Okay, or rather we would say this is butan 2-ol. Okay, and this other one would be butan 1-ol. Okay, you see their names are not the same. So this little difference in the position of the functional group is what makes it position isomers. Remember, we are counting from here. That's why this is 2, because 2 gives us the lowest number, 3 and 4. And here, if we count from here, 1, 2, 3, we'll be getting 3. So we are choosing 2 instead of 3. We choose the side that gives us the lowest number. And this other part, we count from here, because here will give us the lowest number in terms of numbering of the all. Now, functional group isomerism is when the two structures or more than two structures, okay, the structures have different functional groups. Okay, but somehow their molecular formula is going to be the same. So let us see an example of this. The functional group isomerism. So for example, we have okay. So now who can tell me what is the functional group in compound A and in compound B? Okay, this one is obvious. This is an alcohol. Now in compound B, what's the functional group there? Yeah, someone should tell us. You can also type out your answer. What's the functional group in compound B?
Eta.
Eta, very good. Okay, this O there that is telling us it's what? An eta. So this is an eta. But then how do we know that they are isomers? Their structural formula is obviously different because the structure is different. Now we have to prove that they are isomers by determining that their molecular formula, which is the total number of carbon, of hydrogen, and oxygen in each of them, are the same as well. Now, how many carbon do we have in the alcohol? 1, 2. So C2. How many hydrogen do we have? 1, 2, 3, 4, 5, 6, including the hydrogen in the OH. So H6, and then 1 oxygen. How about for this eta? How many hydrogen? How many carbon? 2 carbons. How many hydrogen? 1, 2, 3, 4, 5, 6. Also 6, and 1 oxygen. So you see, the total number of elements making each of them is the same thing as the one making the other one. Okay, but then when you draw the structure, oh, you're drawing two different things. Now, the next is geometric isomers. Okay, just as the word implies, geometry. It has to do with the kind of isomers that movement is going to determine its difference. Okay. Now they have the same molecular formula, okay, obviously, but different spatial arrangement. So geometric isomerism has to do with spatial arrangement, okay, of the group surrounding the double bond. Remember I said it has to do with double bonds, alkenes usually, okay. So for this geometric isomerism, we have what we call cis. Is someone asking a question? Okay. We have what is called cis and trans isomers. Okay. Cis isomers is when two similar groups are in the same side of the carbon carrying the double bond. So for example, we have these two carbons. Okay. And then we have hydrogen here, hydrogen here, chlorine here, chlorine here. This is a cis isomerism because um the same group, chlorine for example, are in the same side of the carbon. You know, this carbon, it can be, this is one carbon having this, and this other carbon is having this. Now the two are in the same side. Okay, they are in the same lane, so they can either be like this, or they can be in the same side like this, or they can be in the same side like this, or they can be in the same side like this. That is what cis is. Same side. Okay. Now trans isomers means opposite sides. Okay, so for trans, we can use the same um example. Let's say we have a carbon to another carbon. Okay, this time around, if we're considering the chlorine and the chlorine is here, another chlorine is here, this is trans isomerism. These two groups that are the same are not in the same side. These two groups, which is chlorine, they are not in the same side. The two groups attached to the carbon, two similar groups. Always take note of that. Instead, they are opposite of each other. So trans can be like this or like this. Okay. So either like this, or maybe look at the two double bond. One chlorine is here, another chlorine is here. Okay. So when we want to name something like this, okay, when we want to name something like this, we won't just say dichloroethene because that's what this is, but we'll say cis dichloroethene. What's the dichloro from? Because they have two chlorine. Why do we have to say cis? Assuming we don't say cis and we just say dichloroethane, and you say someone should draw the structure of dichloroethane, the person can end up putting the chlorine in anywhere around the two carbons. Okay, what if the person draws a trans structure? So at the end of the day, that's the importance of making it cis, writing it as cis or trans. Now let's go back to one of the past questions I showed earlier. Now we say consider the following compounds. Okay, so I hope you can see the screen clearly. Now this compound A, this is a past question. Compound A and compound B are both the compounds that we just dealt with now. So the first question is, what is the relationship between the compounds labeled A and B? Someone should tell us what's the relationship. Based on all we've learned, all I've talked about, what's the relationship between those two compounds?
Chlorine is in opposite side to the carbon in compound A, while compound
Yes.
B, chlorine is on the same side.
Okay, very good. That is telling you that there is cis and trans system going on here, right? Now, let's go back to the question. What is the relationship between the compounds labeled A and B? So if you're writing your exam right now, based on what you've learned, what are you going to write that is their relationship? What are they having in common? That's what relationship has to do with. What's their similarity? What are they having in common?
They have similar
Double
functional
bond.
group.
Uh, Okay, that's very good and observant. But that's not what I'm looking for. What's their relationship based on what you've analyzed earlier? When you say one of them is at this side, the chlorine is at one side, the chlorine is at opposite side. So based on that, what does that tell you?
Okay. The A is having trans configuration, while B is having size configuration.
Very good. So a proper way to really answer this question is say the both of them are geometric isomers of each other. So that your last answer is the correct one. Okay, so they are trans and cis isomers of themselves because their structures are looking different, but because of the positioning of the chlorine, we know that they are isomers of each other. Now, the next question says, name each of the compounds A and B. Okay, I've touched this aspect a bit. So, what are we going to name A? Yes, someone else, someone to tell us. What are we going to name A?
Dichloroethene.
Okay, dichloroethane. But then again, do you know that without your dichloroethane,
This
your answer will not, you won't be given a full mark in WAEC. Yes, someone is saying something. Winner.
is transdichloroethane.
Very good. Trans, okay. Trans 1,2-dichloroethane. Okay, so compound A would be, we first write the trans because now they are asking you to name both compound A and B. So you cannot name A trans dichloroethane. Then if you go to B, you still say the same trans dichloroethane. They can't have the same name. So far, two structures have different structure. They can't possibly have the same name. If you can speak one difference between their structure, their names can never be the same. There must be something in the name that should also differentiate them. Okay, so since these two structures you have identified that one is opposite side, the other one is this, you must include that in the name. Tell us that. Okay, now this carbon is position 1, position 2. So if we say this is trans dichloroethane, okay, ethane. Okay, so the dichloro, what positions are the two chloro? It's in position 1 and position 2. So we can say trans 1,2-dichloroethane. And this will now be cis because it's in the same side. Okay, so this will be cis 1, 2. Take note of between a word and a number is an hyphen. Between two numbers is a comma. Okay, then you say dichloroethane. So you can't really write it like this, 6 comma 1 2 comma, no 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 no. Commas are only between two numbers. Then between a number and a word or a letter must be an hyphen, a dash. Okay, now the next question says, will the chemical properties of compounds A and B be the same? I need someone to give me a brilliant answer for this and why. Will the chemical properties be the same and why will it be the same? We talked about something like this in the previous class. Yes. Will the chemical properties be the same? And why do you say it's the same? You know, in chemistry, if you know something, you have to know why the thing is like that. Otherwise, you actually didn't know it.
Yes, because they contain the same functional groups.
Very good. As easy as that, okay? And what's the functional group there?
The double bond carbon.
Very, very good. Okay, so their properties is going to be, remember when we're defining functional group, okay, we say there are groups that we identify in a structure that makes of that structure have the same chemical properties. So that's why every member of a functional group acts as a family, because they have the same properties. They will act the same way. They will go through the same reaction, chemical reaction. Okay. Now the next question says, give the reason for the answer. Okay, that's the reason. Now this next question is not really on organic chemistry. So go to the B part. The first question says, state one chemical property of ethene or ethine. Let me call it ethine. Okay. So for ethine, when they say chemical property, remember in the last class, okay, don't go mentioning its boiling point, its melting point, it's smelling like this, it's looking like that. No, these are no chemical properties. I told you what makes something a chemical. When we hear chemical properties, your mind should be going to the reactions it's on the go. Those boiling point, this and that, those are the physical properties. Chemical properties means the reaction it undergoes. Okay. Um um its tests, its synthesis, things like that you can also talk about in the chemical properties. So we can give an answer to this. We can say it undergoes addition reaction. Usually, unsaturated hydrocarbons are the hydrocarbons that undergo addition reaction. Okay, that is double bond or triple bond hydrocarbon. They will usually carry out addition reaction to break one of the bonds so that it will now become single. So, for example, an example of addition reaction is, let's say, addition of hydrogen. Okay, so let us use an alkene, for example. An 18 C2H4, okay, we carry out addition of hydrogen is called hydrogenation. Okay, in hydrogenation is when an alkene will alkyne also does this reaction process as well. Okay, not only alkenes. Okay, alkenes carry out hydrogenation reaction to give us C2H6. Okay, so if we want to break this process down, this is the alkene. Okay, reacting with two hydrogens, right? So what happens is this hydrogen comes and it breaks this double bond. When it breaks that double bond, it now makes it spread out to be a single bond. So one of the hydrogen is coming to meet one of the carbon, and the other hydrogen will come and meet it. So it's more like addition of hydrogen to this. So this double bond is no longer being going to be double bond because the hydrogen coming to attach to the two carbons makes this double bond to be broken. So it's now going to be a straight bond. So we have our carbon bonded to carbon, okay? And then our two hydrogens that was in the initial process in the C2H4, and then our hydrogen that carried out the reaction, our H2. One of them will be here, and the second hydrogen will be here. That is hydrogenation. Now there's another reaction called halogenation. Halogenation have to do with halogens, right? That is group 7 elements. So it's the same process, okay? But this time around, we are making use of halogens. For example, bromine. Can be chlorine, fluorine, any halogen. So what happens is it breaks just the same thing hydrogen does. Okay, so one of the bromine will be here, the other one bromine will be attached now to the carbon, the two carbons whose bonds have now been broken. Okay, another one is we also have halohydrogenation reaction. Okay, as the name implies, halogen and hydrogen. Okay, so in this case, one of them will be a hydrogen and the other one will be a halogen. So one hydrogen will be bonded to one of the carbon, and halogen will be bonded to the other carbon. Okay, and also hydration reaction. When we hear hydration, what comes to mind? Water. So it has to do with when has to do with when unsaturated hydrocarbons react with what? With water. Now, if we come back to our question, so like I said, all these examples are usually are for alkenes, okay, but our kinds, the Y, carry out these processes as well. So to answer this first B question, we can write any of these equations. Okay, we can say it carry out um addition reactions to give us on saturated compounds. Okay, or we can say carry out it reacts with bromine water to become colorless. So these are examples of possible answers we can give. And then the next question, what is meant by unsaturated hydrocarbon? We've been mentioning this over and over again in this class. So when we say an hydrocarbon is unsaturated, what do we mean? Unsaturated hydrocarbons are hydrocarbons that have more than a single bond. Okay? They can be alkenes, they can be alkynes. The carbon to carbon bond, mostly. We are not talking about carbon to another element. Do you have any questions so far? Or we are good to go to continue? Let me see a thumbs up if you are good to go. All right. Now the next question is on esterification process. Okay. Now we see that we see complete the following equation. We have seen a carboxylic acid. That's the functional group we can identify here. Sorry. That's the functional group we can identify here. This is a carboxylic acid. Okay. And usually, when a carboxylic acid reacts with an alcohol, what we get is an ester and water. Okay, we can see this is balanced. So that is the same thing we are going to be doing here. Our product will give us ester and water. So we just have to know what ester we are forming and what is the water we are also forming. So now when we see this, we can see that this first one, this is an ethanoic acid, and this is methanol. Okay, so the ester we're going to be forming So an easy way to do this, okay, is since we know that we're going to form water in this equation, we can um, um, remove out what we have used to form our water in the product. It's two hydrogen, which is two hydrogen and one oxygen. Okay. And then our major product would be CH3 COO. Okay, because the hydrogen in the water is donated by the acid, and then the OH in the water is donated by the base, which is the methanol. So what is now left is CH3. So to properly write this out, water is more like composed of hydrogen donated by the acid and hydroxide group donated by the base. Two hydrogens now and one oxygen. That's what makes the H2O. So you just bring out the OH that this one is donating and the hydrogen that this one is donating. Together they make the water. Now what is left that has not been part of making the water is CH3COO and also CH3. Okay, so to name this compound, how do we name this compound? Now you can see the three. They say name the major product formed in the reaction stated above. Now this compound is this CH3, then COO, CH3. So how do we name this? In naming esters, we are going to be the method of naming esters is not conventional. It's not like the common way we name other hydrocarbons or other compounds like this. Okay, it has its own quite different method of naming. Okay, now the first thing is to demarcate this into the two parts that forms our ester. Remember this, in this ester, remember I said this OH was donated by the methanol. So this COO was coming from the acid. No, the hydrogen came from the methanol and the OH came actually from the acid. Okay, so the CO was donated by the acid. So this is the acidic part and this is the basic part. Okay, so the rule is to name first the part after the O. So you look for the functional group first. This is the functional group COO, and then you find a way to demarcate it such that the COO, one of the oxygen is being named with the rest of the compound, and the other oxygen is named with the other oxygen with the carbon is named with the rest of the compound. Now if we are naming, we name the part that goes with the oxygen first. Okay, and this is just met because it's one carbon, right? Okay, and since it's the basic part, we'll call it methyl. And these other parts, okay, we see it's two carbons, so we call it ethane, right? And because of the functional group is O8. So the first part you call the carbon, how many carbon is there? Met. Then the end name will be a il, and for the other one, the end name is a O8 plus how many carbon is there. Okay, so this is going to be methyl ethanoate. Is anybody confused?
I'm confused.
Do you all understand? Okay, you're confused in the naming.
Yes.
Okay, so let me see. Let's name it again. I said the naming esters. So I said the part that is with the O, you name it ending with a ill. And the part that is with the CO, you name it ending with a O8. That's like the parent's name or something like the end name. So let me rewrite it again. This is the this is the compound we got when we do this, okay? So we have CH3, COO, CH3. Now, how do we know the name of this ester? It's better off we draw it. So when we draw it, we have one carbon like this. We have the second carbon. This carbon is to 3 hydrogens. Now we have the second carbon, one to oxygen, the other to oxygen. Oxygen must have 2 bonds surrounding it. Then we have carbon like this. Now this is the structure. So I said in order to name this, we'll look for the functional group. Where is the functional group? Look at the functional group here. The COO. This is the functional group for esters. So what we are going to do, this ester is made of the part that was donated by the carboxylic acid and the part that was donated by the the alcohol part. So I'm saying that if you are to name this, we would divide this functional group into 2 sides, ensuring that one side is beginning from the oxygen and the other side is carrying the carbon and oxygen. So we are dividing the COO into carbon and just oxygen. So there's a group that is following the oxygen, and there's a group that is in front of this carbon and oxygen. So the first thing is to divide into 2 sides. Now this is one side, and this is one side. So we have to name the side and name the side. Okay? Don't be confused. Don't go and start naming the beginning. You will name the side that follows the oxygen. This side. Okay? So this is the side that we would name first. And to name this, we would say, how many carbon do we have? Any naming we are giving to this side, it will end with a "il." And any naming we are giving to the side that is with the carbon and oxygen, it will end with a O8. Okay? So this is what "il" and what O8. The side that is naming with the ending with the oxygen, remember I said is beginning with the oxygen. Remember I said that's the part you name first. So this is it. And this other side is the part you will name next. This is it. So to name this, how many carbon do we have here in this first side of naming? First side. We have just one carbon, so this is a methyl. Now in this second side, how many carbons do we have? We have 2 carbons. You count also the carbon that is making the functional group. So this is ethane. Oit, that's the end name. So this is methyl ethanoate. Let me look for another example. Now, what if we have this? Well, we're going to name this. We are saying that it's an ester because of the COO functional group, right? So to name this, I say we will divide it into two parts. The part where the oxygen is leading and the part where the CO is leading. And the part where the oxygen is leading is the part that we would first name. And this part is the part we will second name. And this part that we'll name secondly will end with a O8. And this other side will end with a L or ill. Okay? So how do we know how to complete the words? This first part, the part that the oxygen is leading, has two carbons. So this is a et, ethyl. While the part that the CO is leading also has two carbons. So that is also et. So we say ethyl ethanoate. So actually, esters have a different nomenclature from the other hydrocarbons. So you have to learn how to name it. Okay? So now what if we have this? Someone else, one of you should name this one for us. Yes, someone should name this. While you're trying to name that, let me draw another one. Yes, who can name the A? Yes. No one. Melody, Winner, and Christine.
Propyl ethanoate.
Very good. Propyl. That's just it. I said the parts that the oxygen is leading, when we divide this, it is like this. So this part, you see this time around, I switched it. Usually this oxygen is part is already at the back, is usually at the back, just as in these examples, right? So you don't have to do this crossing again. The part that the oxygen is leading is the part that you name first. Then before the part that the CO functional group is leading. So the part that the CO is leading must end with a OH, is the one ending the naming. While the part oxygen is leading is the one that is ending with IL, YL. So this is what? Propyl ethanoate. Now what about this other one? This time I'm not going to write the demarcation. You dividing it into two, you get it yourself. So you should try your answer on this one. What would be the name of this ester?
Propyl metanoate.
Very good. Well done, Melody. Yes. I like your responses today, all of you that are participating. So that is what propyl uh, me metanoate. Why? Because when we divide this into two sides, we name this part first and it must end with "il," and name this part and it must end with "a." 8. So this is 1, 2, 3. Propyl. Then this is just one carbon. So it's methan. Okay. So back to where we were. State one way by which the rate of esterification could be increased. Okay, so it can be increased by increasing temperature. Okay. Also by the addition of an acid catalyst, maybe sulfuric acid, H2SO4. Okay, so that's one way. Any one of them use just one. So that is enough for the past question. Let us go back to some IUPAC naming. So we have so many functional groups, okay? Not just the ones that we are limited to. For example, cyanide, CN is a functional group. And we can see this structure here, structure 9. I don't know if it's visible enough for you all. Let me zoom. Okay, remember what we talked about the last time we talked about trends, functional groups with more priority. Okay, so alkyne will have more priority here. And then this last one you can see here. This last one is the same thing as this. We have it as, let me rewrite it out, CH3. Okay, no, let me rewrite it like this, CH3, then bracket CH2, 3. Then we have CH, then they said C3H7, and then we have C2H5. How do you name this kind of a manner of a structure? It's by drawing out the whole structure. Usually, that will help you. So don't just look at it and start trying to name on your own. Now, when we see um things in a bracket, it usually means two things. In this case, it means that there are three CH2. But sometimes you can see a molecule in the bracket. For example, this example when we have CH3, for example, and then we have CH, no, CH3, then we have CH, CH3, then we now have CH3. This particular brackets CH3 is different from what this other one is talking about. This particular one, if we are to draw the structure, we'll say the first one is CH3, right? This is CH3. The second, that is, we have drawn this CH3. The second is CH, then CH3. Now the C, then it's one H. Then this CH3 is telling you that it's attached to the carbon before it. So it's CH3, it's a substitute. Okay? So especially when you see CH3 in a bracket at next to a carbon that is not fully bonded already, it means it's a substitute. It's attached to that carbon before it. Okay? Now, but in this case, we are seeing CH2. So we can have CH2 like this here. It's not up to an alkyl group. So instead, what we have here is we have CH3. That's this first one as CH3. It's the C. Look at the 3H. Now bond to the CH2 three times. So we have CH2, we have CH2, and another CH2. Now the next one is CH. We have C, then one H here. Then the other bond is to C3H7. So we can either say C3H7 or we split it. Okay, we can say CH2, CH2, and then CH3. Okay, but we can write it C3H7. Now again, we have C2H5. We can just write it C2H5, or we can also split it too. Okay, so it's better you split it because that splitting will help you know your longest carbon chain. But either ways, you will also get your longest carbon chain. Now we have CH2 and CH3. So CH2 plus CH3 is still going to give us C2H5. So this thing, splitting it like this, is the same thing as what we have here. Okay, so I've now written out this whole structure that was looking complicated at the beginning. Now, if we are to name this now, what is the longest carbon chain? Yes, I want someone to tell us. How many?
Left to right.
Okay, it's how many? How many carbons makes the longest carbon chain?
7.
No, that is one of the chains that are possible. But I'm asking, what is the longest one? Remember, the rule says the longest continuous carbon chain. So look deep in detail. I've zoomed it in.
8. 8 carbon.
8. That's what's giving us the longest. Because if we are doing the straight chain, don't be confused. Branch chain can also give you longest carbon chain, okay? So if we're doing straight chain, we'll get 7. But that's not the longest. That's long, but it's not the longest. We need the longest. The longest will give us from here to this point. This is the longest. Remember, 3 is here. 3 carbons are here. 3, 4, 5, 6, 7, 8. So this is going to be an octane compound. And these one here now, they will now turn into substitutes. An ethyl substitute. So this is going to be what? What will now be the complete name? This is ethyl. What position is the ethyl? What position is the ethyl?
Five.
No. Remember when we were talking about position, we said we'd choose the one that will give us a smaller number.
4.
4. Are you seeing it? The person that said 5, do you understand how we got 4?
Yes.
Do you understand how we got 4? Now let me show you. We see there are already 3 carbons here. So if we are counting from this direction, from bottom, there are 2 ways we can count. We can either count from this bottom to this other end, or we can count from this end to this bottom. Now let us count from this first end to the bottom. If we count, this carbon will be 1, 2, 3, 4, 5. That means the ethyl group is attached to the 5th carbon. The first counting gives us 5 if we are counting from here. But if we are counting from the bottom, what number will it give us? We already have 3 carbons here, so we'll continue counting. 3, 4. That means the ethyl group is attached to the 4th carbon if we are counting from bottom. So we'll pick the 4th carbon than 5 because we want the lowest possible position. Any side that we'll count from that will give us the lowest number is the side we are going with. That's the rule of naming organic compound, where we give you the possible lowest side. The only time that you will now choose a high number is maybe when there is a functional group. Maybe there is a functional group here. Maybe this place now is not hydrogen, it's OH. Are you seeing it? It's OH. And if we are now counting from this side, this functional group will have to be number 1. It's better for it to be number 1 than for it to be number 8. So we'll count from this side. That is to say, the ethyl group is in the 5th position. Because of this functional group is of more priority, we'll consistently be counting from this side rather than from bottom. So we can count the functional group to be number 1, and we'll now count the ethyl group to be number 4 because we are looking for the smallest number. No, the smallest number focus must be only on the functional group at that period. Okay, so since the functional group we are attaining to be 1, that means we'll continue counting from there no matter how big the position number of any other substituent is. Do you people understand me? If you understand what I'm trying to say, please I want to see a thumbs up if you understand. Okay, Melody understands. Christine understands. Yes. Winner, don't you understand? If you don't understand, let me know. Okay, while we wait for Winner, we have about 5 minutes to the end of this class. So if you have a question, start asking them now. Remember the last time I said you people should come prepared with questions and things like that. So if you have a question, what's your question, please? No question? Okay. What's the
Compound
name
I
of the
just
compound I
drew as
just
well.
drew? Okay, so this compound now is going
Yes.
to be 4-ethyl octane. Why is it ethyl? Because the substituent is having 2 carbons, so it's ethyl. Okay. So for our next class, we'll be learning sorry, please excuse me. Let me confirm the topic so that you will go and you will prepare questions. Okay. You will also prepare for the class. Okay, acids and bases. Although I've not gotten the document, but uh, in order to not waste our time, we're learning acids and bases. We'll learn some calculations in acid base titration process. Okay, types of bases, um, types of acids, and probably we'll also include salt. Okay, and examples of them. And now to detect which is which, and 1 or 2 calculations on um, titration process or on acid and base calculation. Okay, so that's the end of our class today. If you have any question, you can ask. Okay, now I like this particular question. Let's round up today with this question. Okay, so this is the structure. What is the name for this structure? York should attempt it. Let's see the first person to get it correctly. Obawumi, you're thinking. So today's class, we have Melody, we have Rina, we have Kristen. Wumi, what are you thinking? So we will use some knowledge from the last class to be able to answer this one. You just look at the question. You're seeing many functional groups there. You're seeing all the number of carbon atoms there. It's easy to know the longest carbon chain. So you just name it like that. Any attempt? Yes, winner. We Melody and Christine. What did you get? Is this one difficult? Melody and Christine. Winner is already telling me that she got that are thinking emoji. Anytime she uses thinking emoji, that means the thing is taxi. Not as if she can't answer it, but it's threatening her. So she might need one more time to be able to um sort it out. So the other two persons, yes. What's the main functional group in this structure? All right, in order to not take much more of my time, when we see the structure, the priority is falling to carboxylic acid. Remember when we wrote that trend, carboxylic acid is the number one, is at the top, so it will have the most priority. So if we are naming, we already know that this is 1, 2, 3, 4, 5. So this is going to be a pent. What will be the parent name? It's a pentanoic acid. But then we have an OH group here and an OH group here. Okay. Now, in this case, this OH and OH are not going to be presented here as a parent calling functional group. Okay. They're just going to be called as a substituent. So we have 2. This is in second position and the fourth position. So we have 2, 4. Okay. Dihydro. Um, yes. Dihydro, dihydroxyl pentanoic acid.
Ma,
Okay.
oh,
So yeah, you can see it
ma,
here.
why
Yes.
hydrogen?
Why we have hydroxyl
Yeah.
is the OH group, the hydroxide group, the OH. You know, the alcohol group is called hydroxyl group.
Okay, yes, I understand.
Yes, it's called hydroxyl group. Okay. So all these groups, they have name. Just like when we see two strokes, that is, we know we call this double bond. Okay, what should I example? So that's it. So when it is not the major man, like in this case now, pentanoic acid is the one of more priority. When it's not of more priority, it's now going to be like a substituent. So we are not going to call it alcohol. We're going to call it hydroxy. No, we can't call it diol. We can't call it diol. It can only be called all when it's the parents, when it's performing there as the main functional group, when it's the parent functional group. So it can be in between as a substitute and be called all. So we can't say 2,4 diol pentanoic. No, it can all this all can only appear at the end of the name as a suffix. Okay, so but when it's not at the end, the name is no longer called all, it's now called hydroxyl. That is to say, we are now identifying it as OH group, not OH functional group. Okay. All right. Bye bye. Thank you.